I think now we'll move on, okay, because this slot is only for another 45 minutes or so. There are some topics that I want to discuss, so we'll move on. Okay, yeah. So what I was telling, so in some of the lab classes, which is for the next 3-4 days. So since no labs will be held, I will hold theory class also, and so that we can cover up the portions. Okay. Now, so in the last class, what did we discuss? Last class we discussed about Heisenberg's, sorry, no, we didn't discuss. So in the last class, what we discussed was the following. So we looked at the wave nature of the particle. Whoever were present during the offline classes, you would have realized that I was discussing the following. So therefore, just let me recollect that and then move on to Heisenberg's uncertainty principle. What did we do was, so we just summarized everything in one small table. Okay, can you see here? I summarized everything in one small table. Okay, so we take the entity of interest and we ask whether the given entity has exhibit particle nature. If the answer is yes, you have to give an example where it happens. And you will also ask whether a given entity of interest exhibits wave nature. Okay, for example, if I take this part and if I put it in, say, paint accessories, yeah, paint. Check whether someone has joined newly. Yeah, all are fine. Okay, pa. So I think let's come back. Okay, so can you see here, the last class what did we discuss was, I made a small table and we considered light. For example, if I go for a big brush. Yeah, see, for example, I took light. I asked whether the light exhibit particle nature. Does the light exhibit particle nature? So the answer is yes, because in photoelectric effect, light behaves as particle. Next is, does the light exhibit wave nature? Answer is yes, because in interference and diffraction, light behaves as waves, so which could be explained in terms of wavelength, frequency, and phase of the wave and amplitude of the wave. Likewise, if I take X-rays, X-rays are known to exhibit wave characteristics. For example, X-rays will also undergo diffraction. Okay, in the last offline class, I already told about 100 years back itself, people were using X-rays to detect fractures in the human body. Okay, so therefore X-rays was known to exhibit diffraction. Okay, next question is, does the X-rays exhibit particle nature? And the answer turns out to be yes, because in Compton effect, Compton was able to show that X-rays will behave as particle. So light is part of an electromagnetic spectrum, X-ray is also part of an electromagnetic spectrum. So therefore, both put together, I call this as radiation. From this, what you conclude? From this, we conclude that radiation will behave both as a particle as well as a wave. Okay, you can see here that radiation will exhibit both wave nature as well as the particle nature according to my table. Next, if I take electron, electron is known to behave as particle. For example, during radioactivity, the beta particles that are coming from the radioactive nucleus, they are nothing but electrons. So electrons were known to behave as particles. Electrons were known to behave as particles. Okay. Electrons were known to behave as particles. Next question is, does the electron exhibit wave characteristics? Okay, we want to know whether electron exhibits wave characteristics. Okay, so answer turns out to be yes. And who was the first person to predict this? The first person to predict this was De-Broglie. So De-Broglie predicted that electrons will behave as particles, and later, say once it is been predicted by De-Broglie, after some 5 or 10 years, Davison and Germer were able to show that electron will exhibit wave characteristics. Okay, so therefore the fact that electron will behave both as a wave as well as a particle, it was predicted by De-Broglie. It was predicted by De-Broglie. So therefore, this we call it as what? De-Broglie's hypothesis. Now, what is De-Broglie's hypothesis? Let us come to this PDF file. So what is De-Broglie's hypothesis? Look here. This is, yeah, this is sir. What is De-Broglie's hypothesis? Can people see here?
Yes, sir.
Yes, sir, we can see.
Yes, pa. See, people should join within time, pa. Okay, every time I can't give admitting. Yeah. So let us look what is De-Broglie's hypothesis. Okay, so what is the statement of De-Broglie's hypothesis? De-Broglie's hypothesis states that after observing the dual nature of radiation, so De-Broglie put forth an hypothesis which is called as De-Broglie's hypothesis. What does it tell? So it states that nature loves symmetry. If entities such as radiation, if they can behave as particle under certain circumstances, and if they can exhibit as waves under certain other circumstances, then one can expect entities which are ordinarily behave as particles to exhibit properties that are attributable only to waves under certain appropriate circumstances. Okay, once again I'll repeat. What does De-Broglie's hypothesis states? De-Broglie's hypothesis states that nature loves symmetry. If radiation, nature loves symmetry, I think I'll undo. Yeah. De-Broglie's hypothesis states that nature loves symmetry. So if nature loves symmetry, if the radiation behaves as particle under certain circumstances and as waves under certain other circumstances, then one can expect that entities which ordinarily behave as particle to exhibit wave characteristics, to exhibit properties that are attributable to only waves under certain appropriate circumstances. Okay, therefore, just to summarize, what does this tell? To summarize, De-Broglie's hypothesis states that electron which is known to behave as particle, it will also exhibit wave characteristics. Okay, so next is, what are matter waves? Matter waves are the waves associated with a moving particle. Okay, I think the statement of De-Broglie's hypothesis is clear. It just tells that electron which is known to behave as particle will also exhibit wave characteristics. So this prediction is called as De-Broglie's hypothesis. Okay, so this entire table has been summarized into one statement, which is this, and this statement we call it as De-Broglie's hypothesis. So this statement is called De-Broglie's hypothesis. Okay, I think people can understand. Okay, next we will look at what is De-Broglie wavelength and what is the concept of matter waves. So from this figure, can people see De-Broglie's wavelength? So what is wavelength? Can you see here? I think I'll just take this part. Yeah. Say copy, move to paint. Yep, I think I'm just going sequentially. Okay, can you see here?
Yes, sir.
Yes, sir.
So can you see here? So if the particle is in motion, waves will be associated with the moving particle. So that wave is given by this expression here. Can you see here? So this is where, this is what I have encircled here. This is nothing but what? The waves associated with the moving particle. And what do you see? See here, if I draw for example here like this, can you see here? This is a wave. This is a wave where the amplitude is constant. Can you see here? The height, maximum displacement is constant. Can you see here? The height, maximum displacement, this is constant. Okay? The height or maximum displacement is constant. But here what happens? Can you see here? If I take for example here, okay, for example, if I fit a x-axis to this, okay, here this is an example of an amplitude modulated wave. Okay, why it is called as amplitude modulated wave means, see, the amplitude will vary from one wave to another wave. For example, look here, here the amplitude is small, here the amplitude is large, and here the amplitude is smallest. Okay, for example, look here.
So somebody is waiting in the lobby.
Yeah, I think no one is there.
Mohammed Yusuf is saying that he is not in the meeting. He
got the link, right?
Yes, sir. He is waiting, it seems.
Okay, ask him to log in again, because now I'm waiting for him to admit. Participants, yeah, I think no one is there, because if someone is waiting, it will pop up. Ask him to log in again. I'll permit. Okay. Yeah.
Yes, sir. I asked him.
Yeah. Is there?
No, sir. I asked him to log in again.
Yeah. Just ask him to log in. It will pop up. Okay. Yeah. I think this is not required. The initial 5 minutes over. This one not required. Yeah. Let me come to our academic content. Okay. Yeah. So can you see here? Redo. Yeah. Can you see here?
Yes, sir. We can see.
Yes, sir.
Yes, sir.
Yeah. I think I'll. Okay. Has he come, Muhammad? Not yet. Okay. I think we'll move on. Okay. Can you see here? Yeah. Control Z, undo, Control I, redo. Yeah. Okay. Great. Okay. Can you see here, violet line that is coming up? See, for example, here the amplitude is something. For example, it may be say 20 watts. Here it is more. For example, 25 watts. In this place, the amplitude is, in this place, can you see? In this place,
yes,
the amplitude is, say, 5 watts. Okay, therefore, in a matter wave, what happens? The case of a matter wave, amplitude will vary from pulse to pulse. Okay, the case of, see, the amplitude will vary from one pulse to another pulse. Okay, for example, I think I can sequentially show. Look here, for example, here the amplitude will be the highest. For example, I will call it as 25 watts. Here the amplitude is small. For example, it is 20 watts. Here it is still small. For example, 15. Here it is 5. Okay. Yeah, he has not come. Muhammad has not yet come. Okay. So, and so on. So therefore, can you see here? For example, here the amplitude is large, which is say 25 watts. Here it is small, 20 watts. Here it is 15 watts. And here it is 5 watts. And in the last pulse, it will be hardly anything. So therefore, what are matter waves? Matter waves are the waves associated with a moving particle. What are matter waves? Matter waves are the waves associated with a moving particle. They are called as matter waves. In signal processing, this is nothing but what? An amplitude modulated wave. In signal processing, it's nothing but what? An amplitude modulated wave. Okay. So what are matter waves? Matter waves are the waves associated with a moving particle. They are called as matter waves. The wavelength of the matter wave is given by lambda is equal to h divided by momentum, where p is the momentum of the particle. Okay, so where p is the momentum of the particle. So therefore, look here, to define matter wave, actually how many beats are required? This part you also call it as what? Beat. Okay, so what I have written here, no, yellow color line, it's nothing but it is goes by several names. It is called as wave packet, matter wave, beat, then it is called as pilot wave, and so on. So to define de-Broglie wavelength, to define de-Broglie wavelength, how many matter waves you require? So look here, this entire length is there, no? This entire length is actually, this entire length is what? This is actually de-Broglie wavelength. So to define de-Broglie wavelength, how many wave packets you require? You require 2 wave packets. This is the first one, and the second one will be there. It is, although it is not there, but it is clear. Okay. So to define de-Broglie wavelength, how many wave packets are required? To define de-Broglie wavelength, 2 wave packets are required. So therefore, what is that de-Broglie wavelength given by? The de-Broglie wavelength is given by lambda is equal to h divided by momentum, or the de-Broglie wavelength is going to be inversely proportional to momentum. That's all. Okay, I think the idea is clear. So what is de-Broglie wavelength is already clear. What is de-Broglie wavelength? To define de-Broglie wavelength, how many matter waves you require? You require 2 matter waves. What are matter waves? Matter waves in signal processing is also called as amplitude modulated wave. So the waves associated with a moving particle is called as matter waves. The wavelength of the matter wave is given by lambda equal to h by p. As you can see in my figure here, to define de-Broglie wavelength, you require 2 beats or 2 matter waves. Okay, so this concept is clear. Okay, so next what we will do, I think now we will move on to Heisenberg's uncertainty principle, and then we will show that an electron cannot exist inside the nucleus of an atom. Okay, so next this part will come. So what is that? Look here. For example, I'll take this. I think we'll finish this derivation, and then next class we'll move on to Heisenberg's uncertainty principle. Wants to join now? No one has come back. Okay, yeah, I think now we'll move on to the stuff. Okay, so look here. Yeah, so the fact that the electron can behave as waves was predicted by De-Broglie, and it was experimentally proved by Davison and German, and also by Parrott-Thompson later. Okay, so they demonstrated that in an experiment called Davison and Germer experiment, they demonstrated that electron will undergo diffraction. So diffraction is the property associated with waves. So the other names that are given for matter waves are de-Broglie waves, pilot waves, wave packet, and so on. Okay, so in this experiment, so the details of the experiment is not there in the syllabus. Just to give you a gist of it, what I would like to tell is, so in this experiment, they will find the wavelength of an electron using using Bragg's law of diffraction, and you will see that the value of de-Broglie wavelength, that the value of the wavelength that they arrive based on Bragg's law of diffraction, that will match with De-Broglie's hypothesis. Okay, therefore by this one can show that electron will behave as wave, and also the De-Broglie's hypothesis will get validated. Okay, the details of this experiment is not there in the syllabus. Therefore, we'll just move on to one important thing called as the De-Broglie's, the wavelength associated with moving electron. You call it as De-Broglie wavelength. So that derivation we'll do now. Okay, so we'll focus on the wavelength related to De-Broglie's. If electron is in motion, the waves associated with the moving particle, the waves associated with moving electron. So that De-Broglie wavelength, we are now going to derive it. Okay, so what we are now going to derive? We will derive an expression for De-Broglie wavelength of accelerated beam of electrons. Okay, now look here, I think we'll move on to this derivation. Paint is okay, pa. Now look here. See, suppose I draw a conductor. Okay, what is this? For example, this is a copper wire. Okay, this is a copper wire, and this copper wire is now connected to a battery. Okay, and this is the plug key. And people see here, no, look here. This is plug key, I will call it as S. This is the battery of voltage capital V. What is capital V? Capital V is the voltage that you have applied to the conductor. Okay, for example, it may be 1.5 volts or 3 volts of a coming from, say, Nippo battery, Nippo or Dell. Okay, so now look here. If this conductor is connected to a battery, okay, so what will happen? So you know that electrons will be present, free electrons will be present inside the free electrons will be present inside this conductor. What will the free electrons do? The free electrons will move towards positive plate, okay, because electrons are negatively charged, therefore they will get attracted towards the positive plate. So therefore they will move, as per my diagram, they will be moving towards left. Okay, so therefore now what is our goal? Our goal is, we want to find, so if the electron is set into motion inside an electric field, we have to find the De-Broglie wavelength associated with a moving electron. Therefore, how do we do? So look here, step 1, draw the figure. Step 2, close the circuit and apply the potential. Step 3 is what? Find the kinetic energy. Step 4, eliminate velocity and find De-Broglie wavelength. Okay, therefore, how are we going to do? Step 1, draw the figure. Step 2, close the circuit and apply the electric field. So if you apply electric field, electrons are set into motion. Then step 4, find the kinetic energy of the moving electron. Step 5, find De-Broglie wavelength. Done. So therefore, let us do this one by one, step by step. Okay. You see here. So if I close the circuit, what will happen? Electrons are set into motion towards the positive plate. Electrons are set into motion. They will move towards the positive polarity. So therefore, look here. So yeah, I think now we will move on. Yeah, I'll take this. So I'll take this content. Is it somewhere here? Yeah. Okay, pa. I think people can see. People can make out. Okay. What is that? Yeah. For example, if I use, say, blue color. Yeah. So look here. If I close this circuit, what will happen? Yeah. If I close this circuit, what will happen? Electrons will be moving from left to right. Okay. So therefore, what happens? The kinetic energy of an electron of mass m and charge e, that is accelerated in a potential v. So that is given by, okay, can you see here? If I close this circuit, what will happen? Electrons are set into motion towards the left side. Okay. Again, I'll repeat. If I close the circuit, what will happen? Electrons will be moving towards left side. So therefore, what happens? The applied electrical energy is completely converted into kinetic energy. So what do you see here? If I close the circuit, you are applying electric field. So what is the effect of it? Electrons are set into motion. So therefore, the applied electric field is completely converted into kinetic energy for the electron. So therefore, that is what is being given here. So the kinetic energy of an electron of mass m and charge e, so that is accelerated through a potential of V volt. So that is given by what? Half mv square is equal to E into capital V. Okay, what does that mean? Look here, can you see here? I think I'll Focus on just this expression here. Can you see here this expression? What is the left hand side? Left hand side of this expression. What is the left hand side of this expression? It is the output. That is the energy, the electrons are set into motion. So if the electron are set into motion, what is its kinetic energy given by? Half mv square. Half mv square. Now what is the applied input energy? Applied input energy is nothing but it is the electrical energy. Electrical energy comes on the right hand side. So electrical energy is nothing but charge into potential, which is small e into capital V. Small e into capital V. Okay. So once again I'll repeat. If the potential, if the electric field is closed, if the circuit is closed, you have applied the electric field. Applied electric field is given by right hand side, which is E into capital V. That will be equal to, that will be used to make the electron to be in motion. Therefore, the applied electrical energy is completely converted into kinetic energy, which is given by half mv square. Therefore, I will get this equation 1. Okay, so therefore, let me take this part. Let me just take this part and place it here. As I zoom it, I will call this as my equation 1. I'll call this as my equation 1. Okay, this is my equation 1. Okay, next what happens? Okay, so next look here. So in this equation, what I will do is, so I will, now what is the momentum given by? Momentum is mass into velocity. Okay, so therefore, using this equation and this equation, we will have to eliminate velocity. Okay, therefore, let me take the momentum of an electron. Momentum of an electron is given by P is equal to m into velocity. So place it here. Yeah, this is, I'll say I'll call this as equation 2. So I'll call this as equation 2. Okay, what is 2? 2 is nothing but momentum of an electron. Now let me consider equation 1. So here V is velocity, capital V is the applied potential. Okay, what is momentum given by? Momentum is given by mv is equal to mass into velocity is equal to momentum. Now using 1 and 2, what I have to do is eliminate velocity V. So to eliminate velocity V, what we are going to do, look here. So I will multiply both numerator and denominator on left hand side by m. Okay, so if we multiply both numerator and denominator by m, place it here. See in equation 1, so this is equation 1. This is equation 1. Here if you multiply both numerator and denominator, both left hand side and right hand side by m, what you are going to get? Here you are going to get m square. This is going to be m into EV. Okay, so therefore multiply both equation 1 and 2 both on left hand side and right hand side by momentum, sorry, by mass. What you are going to get? What we are going to get is this. Okay, can you see here? Yeah. Place it here. Yeah, let me place it on the side. Yeah. Can you see here? If I multiply both numerator and denominator, by m, what I am going to get? Numerator it is going to be m square v square. In denominator it is going to be 2 by m. Okay, that will give rise to this expression. M square v square by 2m is equal to E into capital V. It's nothing but the same equation. I have just written multiplied both numerator and denominator by m, so that here you will realize that m square v square is nothing but momentum square of momentum by 2. Okay, so fine. Where are we now? Yeah, if you multiply both numerator and denominator of left hand side by momentum, we get m square v square by 2m, which is equal to E into capital V. So which is this. Now what is m square v square? Therefore, what is m square v square? So this 2m when it comes on this side, and 2m when it comes on this side, it's going to be what? M square V square by 2m is equal to 2m into E into capital V. So when it comes on this side, what you are going to get? M square V square will be equal to 2m small e into capital V. That's precisely is this relation. Okay, can you see here? Yeah. What does this imply? This implies that, yeah, this implies that m square V square is equal to 2mv. 2mv. How do I get this? Simply transforming this 2m on this side. We'll get m square V square is equal to 2m E into capital V. But what is m square? What is mv? It's nothing but momentum from left hand, from equation 2. From equation 2, what is m into v? It is momentum. Correct? It is momentum. Can you see here? Yeah. So therefore, now look here. What is p square? M square V square is nothing but square of momentum. Therefore, p square will be equal to 2m E into small v. Therefore, look here. I place it here. Yeah, I think people can see. See, this quantity is nothing but what? From equation 2, it is momentum. Therefore, from 2, this equation can be written as what? P square is equal to 2m E into capital V. Therefore, what is momentum? Momentum will be equal to square root of 2m into capital V. Therefore, what is momentum? Momentum will be equal to 2m into square root of E into capital V. So that is what will precisely come here. Okay, can you see here? The momentum is given by P is equal to 2m E into small v. So I will place it here. Okay, I think this is clear. Yeah, this is clear. So once you know momentum, what is De-Broglie's relation? De-Broglie's relation is lambda equal to h by p. Put that value of momentum from there to this expression, and if you reorganize the terms, we'll get this result. Okay, therefore now look here. What is De-Broglie wavelength of the accelerated beam of electron given by? De-Broglie wavelength is given by lambda is equal to h by p. Okay, so yeah, De-Broglie wavelength is given by lambda is equal to h by p. Okay, so if I call this as say equation 3, so from this equation, put the value of momentum here. Put this value of momentum here, then you will get lambda will be equal to h divided by square root of 2m into E into capital V. Okay, so what you have to do, put the value of momentum from 3 below in the denominator. If you do, what you are going to get? So we will get the following. Okay, so we will get lambda is equal to, we'll get lambda is equal to we'll get lambda is equal to h divided by square root of 2m E into capital V. Okay, now plug in the values of the standard constants. Look here, Planck's constant h is 6.6862 into 10 power minus 34. Mass of the electron is 9.1 into 10 power minus 31 kg. Charge on the electron is 1.6 into 10 power minus 16 minus 19 coulomb. Okay, therefore can you see here the Planck's, if I substitute all those values here, then what we are going to get? Put all those values. So what is the value of Planck's constant? Planck's constant is given by 6.625 into 10 power minus 34 joule Kelvin divided by square root of mass of the electron is 9.1 into 10 power minus 31 kg then what is the charge on the electron? It is 1.6 into 10 power minus 19 into capital V. What is capital V? Capital V is the applied potential. So based on this, if we do, based on this, by plugging in all these values, what we are going to get? We are going to find that the de Broglie wavelength of accelerated beam of electrons is given by this expression. Is given by this expression. That is lambda is equal to h 1.228 into 10 power minus 9 by square root of capital V meters. Okay, so this is a small derivation, and later you will see that this value of the de Broglie wavelength will actually match with, this is derived based on DeBroglie's hypothesis. This will actually match with what has been done using the what has been derived based on the Bragg's law of diffraction. So since both of them match, by this we conclude that the electron will behave as particle, electron will behave as wave. Okay, I think I will stop here now. If anyone has any doubts, you can raise, you can ask, you can unmute your mic and ask me any doubts you have.